Selective coordination in an electrical system refers to the design practice of ensuring that only the circuit breaker closest to a fault opens, preventing unnecessary outages in other parts of the system. This is particularly critical in emergency systems, such as those found in surgery clinics, where a loss of power can have severe consequences. When wiring a surgery clinic with a 277/480 volt service and a 225 kV amps transformer stepping down to 120/208 volts of distribution panel, it's important to understand how far back selective coordination needs to extend to be effective. The goal is to ensure that if a fault occurs on a branch circuit fed by one of the emergency system's 3 branch panels, only the breaker protecting the specific branch circuit trips, leaving the rest of the emergency system operational. Similarly, a fault at the transfer switch should only trip the breaker feeding the transfer switch, and not breakers further upstream. Selective coordination typically needs to extend back to the breaker in the main distribution panel, or MDP. This is because the MDP breaker is the ultimate upstream protection device for the entire emergency system. If a fault current is high enough and coordination is not achieved, the main breaker could trip, shutting down the entire emergency system, which is precisely what selective coordination aims to prevent. To achieve selective coordination, the time current characteristics, or TCC curves, of all the breakers in the emergency system must be analyzed. The TCC curve shows the amount of time it takes for a breaker to trip at different levels of overcurrent. The breakers are selected and configured so that the downstream breakers trip faster than the upstream breakers for any given fault current level. This ensures that the downstream breaker clears the fault before the upstream breaker has a chance to trip. Several factors influence the selection of circuit breakers for selective coordination. Firstly, the available fault current at each point in the system must be determined. This requires a short circuit study, which calculates the magnitude of fault current that can flow at each location under various fault conditions. The fault current is highest at the transformer and decreases as you move further away due to impedance in the conductors and equipment. Secondly, the interrupting rating of each breaker must be sufficient for the available fault current at its location. The interrupting rating is the maximum fault current that a breaker can safely interrupt without being damaged. Thirdly, the breakers must be properly sized for the loads they serve. This involves calculating the continuous load current and selecting a breaker with an appropriate ampacity rating. NEC section 700.27 addresses selective coordination in emergency systems and outlines requirements. It states that emergency systems shall be designed and the overcurrent protective devices selected so that the selective coordination is achieved. Selective coordination shall be selected based on the available fault current at the line side of the overcurrent device. The code also mandates documentation demonstrating compliance with selective coordination requirements. This documentation typically includes a short circuit study, TCC curves, and a written analysis of the coordination. There are a few common methods for achieving selective coordination. Firstly, using current limiting fuses. Current limiting fuses can quickly interrupt high fault currents, limiting the let-through energy and preventing upstream breakers from tripping. Secondly, using circuit breakers with adjustable trip settings. Some circuit breakers have adjustable trip settings, allowing the time current characteristics to be fine-tuned to achieve coordination. Thirdly, using zone selective interlock or ZI. CSI is a communication system between breakers that allows downstream breakers to signal upstream breakers to delay tripping. This helps to ensure that the downstream breaker has time to clear the fault before the upstream breaker trips. Now let's delve a bit deeper into the role of the transformer in selective coordination. The transformer's impedance plays a crucial role in limiting the fault current available at the secondary side. A higher impedance transformer will reduce the fault current, making it easier to achieve selective coordination. However, a higher impedance transformer will also result in a larger voltage drop under load, so a balance must be struck. The transformer's kVA rating also affects the available fault current. A larger kVA transformer can supply more fault current, making selective coordination more challenging. Let's also consider the impact of conductor size and length. Longer and smaller conductors have higher impedance, which reduces the fault current. This can make selective coordination easier, but it also results in a larger voltage drop. Therefore, conductor size must be carefully selected to balance fault current limitation and voltage drop. Now let's talk about the generator. The emergency generator is a critical component of the emergency system, and its characteristics must be considered when designing the selective coordination. The generator's subtransient reactance determines the amount of fault current it can supply. A lower subtransient reactance means the generator can supply more fault current, making selective coordination more difficult. The generator's protective relays must also be coordinated with the circuit breakers in the emergency system. The generator's relays should trip only for faults within the generator itself and not for faults on the downstream distribution system. Now let's discuss some practical considerations for implementing selective coordination in an existing building. Firstly, it's important to conduct a thorough survey of the existing electrical system to determine the existing equipment and wiring. This will provide a baseline for the short circuit study and coordination analysis. Secondly, it may be necessary to replace existing circuit breakers with breakers that have adjustable trip settings or current limiting capabilities. This can be costly, but it is often necessary to achieve selective coordination. Thirdly, it's important to properly document the selective coordination design and to train the facility staff on the operation of the emergency system. This will help to ensure that the system operates correctly in the event of a power outage. There are software tools available that can help with the short circuit study and coordination analysis. These tools can simulate various fault conditions and calculate the fault current at each location in the system. They can also generate TCC curves and help to select the appropriate circuit breakers. The NEC requires that selective coordination studies be performed by qualified personnel. This typically means a licensed electrical engineer with experience in power system protection and coordination. In summary, selective coordination in emergency systems is a critical design consideration that helps to ensure the reliability of power during an outage. It requires a thorough understanding of fault current calculations, circuit breaker characteristics, and the requirements of the NEC. By carefully selecting and coordinating the circuit breakers in the emergency system, you can minimize the impact of faults and ensure that critical loads remain powered. Achieving selective coordination is not simply a matter of choosing breakers with different amp ratings. It requires a detailed analysis of the entire system, including the transformer, conductors, generator, and all connected loads. Let's elaborate further on the short circuit study. A short circuit study is a fundamental step in designing a selectively coordinated electrical system. It involves calculating the magnitude of fault current that can flow at various points in the system under different fault conditions. This information is crucial for selecting circuit breakers with adequate interrupting ratings and for determining the time current characteristics needed for selective coordination. The short circuit study typically considers several types of faults, including three-phase faults, phase-to-phase faults, and phase-to-ground faults. Each type of fault can result in different levels of fault current, and the study must account for the worst-case scenario at each location. The study also takes into account the impedance of all components in the system, including the transformer, conductors, circuit breakers, and any other equipment that can limit the flow of fault current. The impedance of the utility source is also a critical factor, as it determines the amount of fault current the utility can supply. The results of the short circuit study are typically presented in a table that lists the available fault current at each bus or panel board in the system. This table is used as a reference for selecting circuit breakers with adequate interrupting ratings. Now let's discuss the time current characteristic, or TCC, curves in more detail. TCC curves are graphical representations of the tripping characteristics of circuit breakers and fuses. They plot the tripping time of the device against the magnitude of the overcurrent. The TCC curve is a key tool for achieving selective coordination, as it allows engineers to visualize the tripping characteristics of different devices and ensure that they coordinate properly. To achieve selective coordination, The TCC curves of the downstream and upstream devices must be coordinated so that the downstream device trips faster than the upstream device for any given fault current. This ensures that the downstream device clears the fault before the upstream device has a chance to trip, preventing unnecessary outages. The TCC curves of circuit breakers can be adjusted by changing the trip settings. Many circuit breakers have adjustable long time, short time, and instantaneous trip settings which allow the tripping characteristics to be fine-tuned to achieve coordination. Fuses, on the other hand, have fixed TCC curves that cannot be adjusted. However, fuses can still be used to achieve selective coordination by selecting fuses with appropriate current ratings and time delay characteristics. Selective coordination also involves understanding the concept of total clearing time. The total clearing time is the time it takes for a circuit breaker or fuse to completely interrupt the fault current. This includes the time it takes for the device to sense the fault, the time it takes for the device to trip, and the time it takes for the arc to extinguish. The total clearing time is an important factor in selective coordination as it determines how much energy is let through to the upstream devices. The let-through energy is the amount of energy that is dissipated in the circuit during the fault. Excessive let-through energy can damage equipment and cause fires. Therefore, it is important to select devices with low let-through energy characteristics to minimize the risk of damage. Now let's discuss the different types of circuit breakers that are commonly used in selectively coordinated systems. Firstly, molded case circuit breakers, or MCCBs, are the most common type of circuit breaker used in low-voltage power distribution systems. MCCBs are available in a wide range of current ratings and interrupting ratings, and they can be equipped with adjustable trip settings. Secondly, insulated case circuit breakers, or ICBs, are similar to MCCBs, but they have higher interrupting ratings and are typically used in larger power distribution systems. Thirdly, power circuit breakers, or PCB, are the largest type of circuit breaker used in low-voltage power distribution systems. PCB have very high interrupting ratings and are typically used in main distribution panels and switchgear. In addition to these types of circuit breakers, there are also several types of fuses that can be used in selectively coordinated systems. Firstly, current-limiting fuses are designed to quickly interrupt high fault currents, limiting the let-through energy and protecting downstream equipment. Secondly, time delay fuses are designed to withstand temporary overloads without tripping, while still providing protection against short circuits. Thirdly, dual-element fuses combine the characteristics of both current-limiting and time delay fuses. Selective coordination is not a one-size-fits-all solution. The specific requirements for selective coordination will vary depending on the application, the size of the electrical system, and the available fault current. Therefore, it is important to consult with a qualified electrical engineer to design a selectively coordinated system that meets the specific needs of the facility. The NEC provides detailed requirements for selective coordination in emergency systems. NEC Section 700.27, as we have said, requires that emergency systems be designed and installed so that selective coordination is achieved. This means that the overcurrent protective devices in the emergency system must be coordinated so that only the device closest to the fault opens, minimizing the impact on the rest of the system. The NEC also requires that selective coordination studies be documented and available for inspection. This documentation should include a short circuit study, TCC curves, and a written analysis of the coordination. In addition to the NEC requirements, there may also be local codes and regulations that govern selective coordination. Therefore, it is important to check with the local authority having jurisdiction, or AHJ, to determine the specific requirements for the area. Selective coordination is an ongoing process. The electrical system should be periodically inspected and tested to ensure that the selective coordination is still effective. This is particularly important after any changes are made to the system, such as adding new loads or replacing circuit breakers. Regular maintenance and testing can help to identify potential problems before they lead to outages or equipment damage. For instance, infrared thermography can be used to detect hotspots in electrical equipment, which can indicate loose connections or overloaded circuits. These problems can be corrected before they cause a fault. Circuit breaker testing can be used to verify that the circuit breakers are tripping properly and that their trip settings are still accurate. Fuse testing can be used to verify that the fuses are still in good condition and that they have not been damaged. Let's explore the economic considerations of selective coordination. While selective coordination can add to the initial cost of an electrical system, it can also save money in the long run by reducing downtime and preventing equipment damage. The cost of downtime can be significant, particularly in critical facilities such as hospitals and data centers. Selective coordination can minimize downtime by ensuring that only the affected circuit trips, rather than shutting down the entire system. The cost of equipment damage can also be significant. Selective coordination can protect equipment from damage by limiting the let-through energy during a fault. Finally, let's discuss the ethical considerations of selective coordination. Electrical engineers have a professional responsibility to design electrical systems that are safe and reliable. Selective coordination is an important part of this responsibility, as it helps to protect people and property from the hazards of electrical faults. Engineers should always consider the potential consequences of a lack of selective coordination and should take steps to mitigate these risks. In addition to the technical aspects of selective coordination, there are also important communication aspects. Engineers should communicate the importance of selective coordination to building owners, facility managers, and other stakeholders. They should also provide clear and concise documentation of the selective coordination design. This documentation should be easily accessible and should be kept up to date. Now let's delve into the specifics of applying selective coordination in a surgery clinic setting. Surgery clinics have unique electrical requirements due to the critical nature of the medical equipment used. A power outage during a surgical procedure can have life-threatening consequences. Therefore, selective coordination is particularly important in surgery clinics. The emergency system in a surgery clinic typically includes a generator, a transfer switch, and several emergency panels that feed critical loads such as operating room lights, anesthesia equipment, and life support systems. The selective coordination design must ensure that these critical loads remain powered during a power outage. In addition to the emergency system, the normal power system in a surgery clinic must also be selectively coordinated. This is to prevent a fault in the normal power system from affecting the emergency system. For example, a fault in an office area should not cause the operating room lights to go out. The selective coordination design should also consider the potential for future expansion or modification of the electrical system. The design should be flexible enough to accommodate new loads without compromising the selective coordination. Finally, the selective coordination design should be reviewed and approved by a qualified electrical engineer with experience in healthcare facilities. Now let's talk about the transfer switch in more detail. The transfer switch is a critical component of the emergency system, as it automatically switches the loads from the normal power source to the generator in the event of a power outage. The transfer switch must be properly sized and selected to ensure that it can handle the load of the emergency system. The transfer switch must also be selectively coordinated with the upstream and downstream devices. A fault at the transfer switch should only trip the breaker feeding the transfer switch, and not breakers further upstream or downstream. There are two main types of transfer switches: automatic transfer switches or ATS and manual transfer switches or NTS. ATS automatically switch the loads to the generator when a power outage is detected. NTS require a manual operation to switch the loads to the generator. ATS are typically used in critical facilities such as hospitals and data centers, where a seamless transfer of power is essential. MTS are typically used in less critical facilities, where a brief interruption of power is acceptable. Now, let's discuss the generator in more detail. The generator is the heart of the emergency system, as it provides backup power during a power outage. The generator must be properly sized and selected to ensure that it can handle the load of the emergency system. The generator must also be selectively coordinated with the upstream and downstream devices. A fault within the generator should only trip the generator breaker and not breakers further downstream. Generators are typically powered by diesel engines, natural gas engines, or propane engines. Diesel engines are the most common type of generator engine, as they are reliable and efficient. Natural gas engines are a good option for facilities that have access to a natural gas supply. Propane engines are a good option for facilities that are located in remote areas where natural gas is not available. The generator must be regularly maintained and tested to ensure that it is in good working order. This includes checking the oil level, the coolant level, and the battery charge. It also includes running the generator under load to verify that it can handle the load of the emergency system. In addition to the technical aspects of selective coordination, there are also important safety considerations. Electrical work can be dangerous, and it is important to follow all safety precautions to prevent injuries. Only qualified personnel should perform electrical work. Always to energize the circuit before working on it. Use appropriate personal protective equipment or PPE, such as gloves, safety glasses, and arc-rated clothing. Follow all applicable codes and regulations. Be aware of the potential hazards of electricity, such as shock, arc flash, and arc blast. By following these safety precautions, you can minimize the risk of injuries and ensure that electrical work is performed safely.